fired towards the first particle with a velocity of 30 meters per second. 30 meters per second. The separation between them is 1 meter. How close does the second particle come to the first particle before its velocity becomes zero? Now, what is happening here? Why would its velocity become zero to begin with? This particle is given an initial velocity of 30 meters per second. But this particle also has the same charge, 10 plus 10 plus 10. So there's repulsion between them. So there's a force of repulsion. This charge is pushing the other charge away. And as it gets closer and closer, the force of repulsion becomes bigger and bigger because now the separation becomes smaller. So the force of repulsion becomes bigger and bigger and bigger until finally, and of course with the force of repulsion, it means that there's acceleration. It's a negative acceleration. It's to the left, the acceleration. So this is moving, but it has an acceleration to the left. It's like a car moving with the brakes on, with a force acting on it backward. It's moving forward, but there's a backward force acting on it. So what will happen to it? Eventually its velocity will become zero. In fact, its velocity will become zero, and then it will, because of the repulsion, it will start moving in the opposite direction. It will start moving to the left. But our question is, how close does it come when its velocity becomes zero? So at some point here, its v becomes zero. And we want to know how far is this? What is this distance r? Let's call it r. What is that distance? All right. Again, this is a conservation of energy problem. We have two instances. We know the speeds. We know the velocity at both positions. So at the first position, I have the kinetic plus potential energy is equal also at the final position. So K1 plus U1 is K2 plus U2. At the initial position, K1 is half m v1 square plus U1. Now what is U1? Here I have two charges, Q1 and Q2. What is their potential energy? We studied that. It's K, Q1, Q2 over R. So plus K is 9 times 10 to the 9, Q1, Q2 over the distance between them. The distance between them is 1 meter. Let's call it D for now. This is equal to the energy here. Here the velocity is zero, so the kinetic energy is zero. V2 is zero. The potential energy here, again, I have two charges, Q1 and Q2, but now they are separated by a distance r. So plus K, Q1, Q2 over r. The only unknown is r. Everything else is known. So I have, to get r, d is 1 meter. Q1 is 10 microcoulombs. Q2 is 10 microcoulombs. M is given. V1 is 30 meters per second. So the only unknown is r. To get the answer, I can move this here. So this becomes half mv1 square equals K Q1 Q2 1 over R and then minus 1 over D. So this means that 1 over R minus 1 over D is equal to half m V1 squared divided by K Q1 Q2. Let's put the numbers. Half m is 6 times 10 to the minus 3. V1 square, V1 is 30, so V1 square is 900, that is 9 times 10 to the 2, over K, which is 9 times 10 to the 9. Q1 is 10 times 10 to the minus 6, that is 10 to the minus 5. And Q2 also is 10 to the minus 5 coulombs, so that's 10 to the minus 10 altogether. So this is half times, first the 9 and the 9 cancel. Now 10 to the minus 3, 10 to the 2 is 10 to the minus 1. 10 to the 9, 10 to the minus 10 is 10 to the minus 1. So the 10 to the minus 1 cancel out, and I'm left with half times 6 only, which is 3. So 1 over R minus 1 over D, but D is 1 meter, is 3. So this means that 1 over R is, this is just 1 minus 1, take it here, 3 plus 1 is 4. So this means that R is 1 over 4, 0.25 meters. Okay? Clearly I adjusted the numbers to get a nice number. So just 1/4. So they are 1 meter apart, and it stops. Its velocity becomes 0 when it's exactly 1/4 of a meter apart. And this ends our examples on the electric potential. Thank you for watching.